Welcome back, and thanks for sticking with the series on the 8086. So what have we learned? At this stage, I want to recap what we've done, what we tried, what we saw, and why we have to change what was built. Fundamentally, the thing I want to get across is the step from an 8-bit processor operation to how a 16-bit processor works. The 8086 is a 16-bit processor. It uses a 16-bit data bus, and it uses a combination of 20 addresses and 16 address lines. We connected one EPROM. We built a binary file containing 3 test lines of the assembly instructions move AL20, move A860, add AL12. We obtained the machine codes for those 8086 assembly instructions B0, B4, 04. We loaded those to locations FFF0, FFF1, FFF2, etc. in the EPROM. And then when we started the 86, it didn't read FFF0, FFF1, FFF2. So all 6 lines, it only read the values in 0, 2, 4. Why? Because it's a 16-bit processor. And in reading 16 bits, it moves FFF0, then FFF2. So we need a redesign to use 2 EPROMs with a high bank and low bank. But not only that, we found, and the datasheet told us this, the 8086 uses the A0 address line to access the D0 to D7 lines and the BHE to use the D8 to D15 lines. So this is a huge difference, and we can't use the A0 address to connect to the EPROMs. We have to use A1 to A16. Therefore, this is our overall design. Here we have the address latches with the 16 address lines, but here from the output of the latches, we're only going to use A1 to A15. A0 is not used anymore. We're going to have an EPROM low and EPROM high, and here the EPROM high will have the data lines connected to AD8 to AD15. The EPROM low will have the AD0 to AD7, and we will use 16 address lines to address these 2 EPROMs. I'll therefore have to move components around to add the second EPROM whilst leaving space to add my LCD display. This is the LCD display I intend to use. You can get it in green and blue, and it's only a few quid on eBay. You can see it actually uses data lines D0 to D7, so 8 data lines. It's actually a 1602, and the idea is I'll connect that to the 8086 breadboard and we'll display the hello world on this. So I'll need to make room on the breadboard and reposition the components on the board to also make room for this. So I'm going to have to start by removing the EPROM and the address and data lines and repositioning them, and then I need to be able to remove the EPROMs so I can easily program them. So I'm going to move these over to this side so I can get at them, and then I'll need to start by moving these power lines over to the other side. So I'll take this positive line out from here, move that over to this side out of the way. And the negative line also over to here. I then need to connect, well, let's get rid of the board here, the slot board. And then I'm going to put one EPROM here, move the EPROM over, and then maybe have some room for the logic on this side and then the LCD display. So I need to remove all of these data lines. And then all these address lines. And obviously, chip enable line, the data lines, the read, the power, and all these address lines and this EPROM. So rather than you watch me take this all apart, I'll come back in the video where I've moved all these address lines and put the EPROMs back in place. So I've connected the two EPROMs onto the board. I've also connected the power supplies to the EPROMs, the +5 and the negative rails. And now I need to start connecting the latch outputs from A1 through to the EPROM A0. So that's pin 5 to pin 10. So if we go 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the EPROM, which is A0. And then to pin 5, 1, 2, 3, 4, 5 on the latch. And 6 on the latch. To 9. 9 on the latch. Okay, 12 on the latch, and that's going to be 10, 11, 12. $15 on the latch. It's 12, 13, 14, 15, so that's just in there. 11, 12, 13, 14, 15, just in there. $16. 11, 12, 13, 14, 15, 16. 19 on the latch. And then 2, which is obviously within this latch, connects into the last 7 lines. So 2 on that second latch to there. So that's the first 8 lines connected, or first 8 address lines connected. And then we'll move on to the next ones. Okay, and now we have the last 4. So 2 to 15, 26 to 16, 27 to 19, and then this A16 line. So 2 on the EPROM, all the way through to pin 15, 11, 12, 13, 14, 15. Pin 26 to 16. 16 to 26. 28, 27, 26. 27 through to 19. So 19 is in there. Through to 27, and then finally pin 1 on the EPROM goes through to the address 16 line on the 8086. That's because the 8086 A16 line here isn't an AD, so it actually doesn't go through a latch, because these last pins A16, 17, 18 and 19 don't need to be latched because they're not multiplexed. Only the ones 0 to 15 are multiplexed. So that's all 8 data lines connected, or sorry, all 16 address lines connected to the EPROM. So next are the 8 data lines from the microprocessor to the EPROM. I'm going to do the D0 to D7 first. So the D is 0, so it's 16, 17, 16, 15, 14, 13. I'm going to have to go to these Q0, Q1, Q2 on the EPROM. So 16 in here is going to connect all the way across and into here. So I'm not going to try to connect those. I'll do this offline and then come back once I've connected the first 4. So I've just been connecting the data lines. What we have is Q0, Q1, Q2. So that's Q0, Q1, Q2 on the EPROM here, which are connected across onto the 8086 data output lines. You'll see that the data lines here run from 16, 15, 14, so 0, 1, 2, 3, 4. So those are all counting down to there. So 0, 1, 2, those ones there are connected to the 3 inputs here of 0, 1, 2. I've then gone on connected the next ones onto these Q3, Q4, Q5, Q6 on across here, and I just need to connect the last one, which is onto the last D7 line from the 8086 data line onto the EPROM. So that's the data lines D0 to D7, so the 8 data lines from the 8086 to this EPROM. The next data lines will connect from the 8086 to this EPROM, and I need to connect all the address lines from this EPROM to this EPROM, and I'll do that in the next stage. Next, I'm going to connect the data lines from the 8086 through to the second EPROM. The address lines is Q0, Q1 and Q2 are these ones, so I connect those data lines up first. I can't really take the line up through here because I really need to be able to take these EPROMs out when I need to program them, so I can't really have that wire in there. So I'm going to take that out and replace it. This one here. So this is the address line, the A16, which can go directly to the EPROM. So that way I'm avoiding, because I'm going to need to take that EPROM out there and then take that EPROM out, so I can't have any wires really going through there. So I've just rewired that A16 line onto the address line on that EPROM, which is the A15 input. And then I can start doing the data lines. I'm going to do these ones, which is the Q0, Q1 and Q2 first. So the Q2 will go in here, so that's this Q2, and that will go around and into there on the data line. And then the next one will come through and into here, and the next one will come through, and those will be the 3 data lines. So I will do those offline and come back when those are connected. So now I just connect that last line in there. So that's the 3 data lines, Q0, Q1, Q2, Q0, Q1, Q2 connected into the 8086 data lines. And then we need to do Q3, Q4, 5, 6, and 7 along here. Okay, so that's 3, 4, 5, 6, and then last one, 7, has to connect all the way around to AD15, so over on this side. And that's all the higher data lines connected to the second EPROM. So that's D0 to D7 to here, and D8 to D15 connected to that EPROM. Then we need to connect the addresses across. So that's the data lines complete. The address lines are next, and as A0, A1, A2 on the EPROM here and on the EPROM here exactly the same, all I need to do is literally link this A15 here to address 15 on here, A12 on here, so A12 on here, A7 on here, to A7 on here. So you get the picture, just connecting all of those across, and I'll do the rest of those offline. Okay, so that's all the address lines connected to between that EPROM and that EPROM. So that's all the address lines along this side all connected. So I've just extended those ones across to there and completed all of those. Next then would be the address lines, these A14, A13, A8, A9 and A10. So these ones here. So again, very similarly, it's extending this one here to here, and then all the other address lines. But actually before I do that, I want to connect up before we hide all of that, I want to connect up the read pin, and the read goes to this pin 22 and read on the microprocessor from there. So pin 22 is there. And the read pin on the microprocessor is 32, which is there. So that's the read connected. So whenever the microprocessor wants to read, it sends the low read signal to the EPROM. I'll then need to obviously connect that one across to the read signal on there. And then I'll connect the address lines. So I'll come back when I've collected those lines. Okay, so that's those address lines in there. Then we have the read line. So that connects into there and connects across into there. So that, and then finally the very last address line, which is A10, which is in there. And that comes across and connects into there. So that's all the address lines now connected. So we have the 16 address lines connected between the two EPROMs and the latches. We have the data lines connected, the read line, and all we need now is the chip enable. The chip enable then should be able to go from the chip enable pin here to the NAND gate. So I think I should be able to squeeze that through here somehow. Let me see, yep. Put it through there, like that. The output of the NAND on pin 3. And then connect it into the chip enable pin on the EPROM. And then connect the other chip enable on the EPROM, which is in there. And connect that across. And into there. So that's the chip enable connected. We now need to carefully consider the implications of dropping off the A0 address line into the EPROM. This is a very important concept and one to get your head around. You may need to watch this several times to grasp, and if you do, please go ahead and do that. We still need to provide 16 address lines to the EPROM, so although we have dropped off A0, we still need to provide 16 address lines into that EPROM. And we do this by using A16 to A1 instead of A15 to A0. So what's significant about that? Well, let's look at 16 address lines where they're all ones. And that's FFF in hex. So what about FFF0? Well, it looks like that, where the last 4 significant bits, least significant bits, are 0. And we know that FFF0 is where the processor starts, and that's where we've added our machine code. And what we did was we went into the binary file and we added the entries in at location FFF0, then the next one FFF1 FFF2. So it's important to understand what happens now that we've dropped off the A0. So what we have is these addresses grouped into 4. So the first 4, the most significant bits, 15 to 12. Then the next significant bits, 11 to 8. Next one's 4 to 7. And of course the last one. So we're all in groups of 4. But this last one, 0, we're going to drop off. We're not going to actually use that. So although that is FFF0, this least significant bit, this little bit here just at the very end, that which was the A0 line, that's not going to be there. So it's going to look like this. But we can't have that. We need 4 and 4 and 4 and 4. So we need it all in groups of 4. So in fact, what actually happens is because we've switched these addresses, this piece here actually becomes the 4th bit. So this needs to move across. And the 16th bit, the A16 line, comes in at this end. So in fact, they all shift across. So this one will become onto here. So we'll actually get 1, 0, 0, 0, and the 1s and the 1s. So it'll actually look like that. So the bit that was here, which is the 5th bit, has now moved across because we've dropped off the A0. So that's what we're actually seeing. And what does that in hex? That's actually FFF8. So in fact, FFF0, because we've dropped off the actual A0, is actually presented to the EPROM as FFF8. So therefore the EPROM start location is not FFF0 but FFF8, because that's what's being presented to the EPROM, because we've lost that last A0 line. So what happens when we move on to the next location? We went FFF0 and then we go on to FF1. But again, the same thing is going to happen because FFF1, we're going to lose this least significant bit. So it's going to drop off that last significant bit. And what's it going to look like? It's going to look like that. But again, we need to group it in 4s because we need to provide the 16. So the A16 line comes in here. This one will move across to give you the 1, 0, 0. So it looks like that. So it's actually FFF8. So actually FFF0 and FF1 are both address FFF8 now. So where we were writing the information into the process or into the EPROM at FFF0 and then FFF1, we're now going to have to use FFF8. But actually, both locations FFF0 and FF1 are both going to be FF8. So that's what it used to look like for FF0, and that's what it looked like for FF1. But because we've lost these 2 least significant bits here, these have gone and everything's shifted across, they both become FF8. So both addresses are FF8 with A0 now dropped off. And equally, when it moves on to FF2 and FF3, because we've lost that least significant bit, they're actually, both of those, FF2 and FF3, are presented as FF9. And that has big implications when we go to write the binary file and load the binary file into the EPROMs. So now we need to load our 2 EPROMs. Again, I'm going to use the same test data as before. So 3 lines of move AL20, move AH60, add AL12, which machine code is B020, B460, 0412. We know that before we placed that at location FFF0 in our EPROM, but we can't do that now, having dropped off the A0 line. So although the processor is outputting address FFF0, the EPROM sees it as FFF8. So we need to load the EPROM starting at address FFF8. So we have 2 EPROMs, even address. Our EPROM there has data lines connected to D0 to D7, odd, where the data lines are D8 to D15. The start address from the 8086, as we said, is FFF0, but with A0 removed, the EPROM sees this as FFF8. And FFF1 is also seen as FFF8. So we need to create 2 binary files, one for the EPROM connected to the D0 to D7 and one for the EPROM connected to the D8 to D15. And then we need to load the values in. So in fact, these are the values that are going to be read, B0, B4, and 04 by the D0 to D7 data lines, and the other higher data lines are going to read the 20, 60, and 12. So I'm going to create a second binary file. I'm going to call that the ROM 8086 odd, which is the 8 to 15 addresses, so we can identify that. And so here is the code that we originally wrote, which was put in address FF0123. So I'm going to just copy that line. We now need to put this in FFF8. We then need to do the next address, which will be 9. And then the last address, which in sequence is A in hex. And it will have the move AL instruction in this EPROM, which is B0, the move AH, which is B4, and the move and the add AL, which is 04, 04, which just goes to 4. So we can take those out. And this is the file then that we'll create for the ROM 8086. I've added a second button. So when we go and look at this button, this will create the second binary file. So here's the code here. So I'm going to copy the exact same code here and put it into this button. So it's doing exactly the same thing. We said we would call this file ROM 8086 odd 8 to 15. So I'll just change that name in there. And this, of course, will have the other parts. So this will actually, at address FFF8, will have the 20, the 60, and the 12. So now we have the data split between two EPROMs, with the B0, B4, and 04 in one EPROM, and the other higher bits in the second EPROM, 20, 60, and 12. So now when the EPROM reads the line, it will read one from one EPROM and the next one from the other EPROM. It'll move on to the next address and it'll move on to the next address. Let's put that in. 60 and 12. So all it's doing in this second EPROM is loading the 20, 60, and 12 and using the same addresses. So now if we run this, and we hit this would create the ROM file, and we hit this, and that's created the second file. So here I have my XG Pro, the EPROM programmer code. I'm going to load the first ROM into the EPROM. And you see it's full of the 90s. If we scroll down to the bottom, we can see there at the location FFFA, it's got the B0, then 9, it's got B4, and it's got 04 on the other one. If I then load the other file, and again, we look at the bottom here at location 8, there it's got the 20, the 60, and the 12. So when we run the code and look at the data, these are the values we should be looking for. The binary machine code has now been loaded into the EPROM. So now I'm just going to add this EPROM to the board. So the code's loaded on both of the EPROMs. The next stage is to add the reset and clock signals. But before I do that, I'm just going to connect this A16 line here, which is coming from the 8086. Rather than drive it from the A16 output from the 8086, the 8086 has 20 address lines split as top 4 and then 16. As shown previously, the 16 address lines allow the 8086 to work with a 64K block, and the top 4 address lines, A16 to A19, allow it to address 1 meg of memory. For my Hello World program, I'm working in one 64K block with EPROM in the range 8000 to FFFF, so I'm not going to use these top 4 address lines at all. And as A16 is one of these top 4, I'm just going to connect this to high. So this address line will always be 1. Now I'm going to connect the Arduino, as I need to be able to monitor the data line to check the circuit is working, and we can then see the B0, B4, 04 being read by the 8086. So I'll come back when I've connected that Arduino. Okay, I've connected my Arduino. I've got all the data lines, the 16 data lines that's from the 8086 connected to the Arduino input digital lines on the Arduino. I now need just to connect the power supply, so the positive and negative lines. I got the clock signal, which goes in here to the clock on the 8086. So that's to be able to step through. I've got my reset signal, goes on the 8086 for the reset. On the Arduino, I've got pin 2, and because we're running it off the read, I need to connect that to the read line on the 8086, so we can trigger it on the read line on pin 2. I need to get the common ground on the Arduino, and then the USB connection to my Arduino to upload the sketch. Power the board up. and step through the process. So I connect the Arduino, I upload the sketch so we can monitor the data pins. It's done uploading. I then open the serial monitor so we can monitor what's coming out. I connect power to the board and we get some spurious data coming through until we go through the reset signal. And then we let the reset go through the clock signals. And there we go. 20B0, 60B4 and 1204. The test data is coming through and is being read by the 8086. So everything's working. So next stage is move on to adding the LCD and writing some other code to write to the LCD. Brilliant.